Good morning, everyone. I'm really happy to be here. I'm Irina, and as a computer vision engineer, I've helped a number of companies build products that required things like image retrieval, object detection, tracking. Today I'd like to share with you one particular experience, not at Siemens Mobility, but at a Berlin-based startup that wanted to build an augmented reality app for entertainment that required the detection specifically on a mobile device of certain objects. This particular app allowed you to do satisfying things such as this. So to actually punch this guy's head in, you first need to find it and be able to track its position during the video, right? And when you're dealing with people who are using the front camera, traditional computer vision techniques work fairly well. When your subject is facing the camera, they're not far away, that works fairly well. But what happens when you're going to be using the back camera and you don't know what distance your target is going to be, and they're probably not facing the camera, so it's even hard for maybe even a human to know if that's technically a face or a person. At that point, we decided to turn to deep neural networks. This is, if you're hearing a kind of disclaimer here, it's because that's what it is. What I'm saying is we actually turned to deep learning because traditional techniques were failing us. So what we realized at that point is something that Sun Tzu may or may not have said centuries ago, and that's that when you're trying to deploy a network on a mobile device, the work doesn't start with writing native code. It starts way, way before that. So a quick show of hands. Who here has been working with neural networks? Who has deployed on production? Okay, so this pipeline will probably feel slightly familiar to you. I'll keep coming to this slide during the presentation because to me and to the team this was a lifesaver. Specifically because when you're deploying in production, you definitely cannot use black boxes. And one of the critiques to deep learning is that sometimes it is seen as a black box which you cannot control. So that has to stop when you're deploying on production, and more so when you're deploying on a mobile device, because you need to absolutely control every aspect of it. So we'll start with the actual task. We were trying to detect objects. So just to clarify, a detector, you can see it as a classifier plus a localization module. You can see the difference would be like between a classifier proposing labels, what it roughly sees in an image, whereas the detector would be responsible of saying, specifically here is where you find that label. So you see it as, say, Lego blocks. You can see the detector as two Lego blocks, interchangeable to an extent, where the classifying block is responsible for proposing a label, and the localization block is responsible for proposing an actual region, a bounding box around your target label. So as for our constraints, we were targeting iPhones from an iPhone 6 onwards, which meant that we were planning to have maybe a gigabyte of RAM available, but of course shared amongst other apps that could be running at the time, and processing power that is definitely way below what you'll have in a regular laptop. Bear in mind that we wanted to be running this on real time, but not the detector itself, because we were going to be building effects on it using Unity. So that means that our 25 or 30 FPS had to be for the whole app, which means that the detector itself had to be running at about 40 or 60 FPS. So what do? If you see the detector as being largely based on a classifier, you want to compare the known classifiers out there and start with a very light one. And that's what you're seeing in this graph. what we set about was to compare different known models that had competed on ImageNet. Well, if this morning you've seen in the opening speech about how AI has already surpassed human levels in image classification, where we looked at those models that had competed in such challenges, and on the x-axis what you're seeing is the number of operations required to produce a single prediction for an image. On the y-axis, you're seeing the accuracy obtained by that model over ImageNet, and the size of the circles is proportional to the number of parameters on your model, so basically your memory footprint. And with our constraints in mind, we knew that we couldn't go into the red area because that means going into very slow models for what we needed. And as for the size of our model, we were targeting roughly 5 million parameters, which means that almost all of that was way too big, way too heavy for us, except if you notice, the very red dots there are the MobileNet models that were released a couple of months back by TensorFlow, and SqueezeNet is right there, which was also, if not particularly accurate, it had the right size. So once we have a rough idea of what kind of models are going to work for us, we needed to make this more accurate and lighter. So the first step, of course, is to start off with a rough architecture that is known to be light and fast, thanks to the comparison before. Other things that you can apply to reduce the memory footprint is trading layers that add too many parameters to your model for ones that are a bit lighter. Such is the case with fully connected layers that can always be translated into convolutional layers that will make your model a bit lighter. And as for inference time, one thing you want to do is an old trick in any computer vision technique, which is play around with your input and layer sizes. Well, layers more for deep learning, but every step's size you can trade for accuracy. And that's actually a trick that is being used on the MobileNet models, where you have different tiers that respond to different sizes of the layers. Oh, that was, oops, there we go. And as for the detector itself, what affects its size are a number of things. One is the strategy used to produce the predictions, because how many times do you need to process your image to produce a prediction of where different objects are? What you want is that an image is only processed once, such is the case with models such as YOLO. Another trick that you can use is, well, for competitions such as ImageNet, you need to keep track of a lot of different categories, thousands of them. However, does your app really need that? Wouldn't it be enough for your particular case to keep track of 10, 20 categories, even less? That's something that you need to bear in mind when you're going to be deploying for a particular use on a phone. And I just want to sneak a short comment on further tricks that you can apply to your model once you've nailed down the architecture, because the basis of everything is nailing down the architecture, and then before deploying you can still do things like removing layers that you needed during training but you don't need at inference time, pruning nodes, or quantizing your weights. Luckily, a number of those steps are already available out of the box from TensorFlow or Caffe 2. And if you need to squeeze that extra performance, you can always turn to for instance, TensorFlow's XLA. But to be honest, at that point, if you need to delve into that, you're probably better off going back to square one and rethinking your whole architecture to make it lighter. So in any case, when you get to this point, you have your architecture that gets dumped into that configuration file. And at this point, that file is basically, it looks like a proto.txt file from Caffe. It's essentially a description of your network, layer by layer. You get that on your configuration file, and you pass it on through your pipeline. And you're ready to start looking at the data, because it's well known that deep learning requires massive amounts of data, but that doesn't mean it has to be your own, at least not at the beginning. There's a number of openly available data sets that you will want to use to train your network. such as, well, it depends on what your actual application is. If your mobile app is meant for self-driven cars, then you might want to use the Kitty data set, which you can see below. The image below has, with that weird elongated format, is meant for that. But that's not the same as developing an app for entertainment, where you're going to be picturing people pretending to be zombies, like in the image above, or in a very specific format, like the iPhones to the right, where you're just also, for instance, recording sports or family events. It's just not the same thing, and you need to be aware of what kind of data you're going to be receiving. So when you're trying to choose that data, you want to keep track of the intended use, and yes, overfit for that use, because it is helpful and it will save resources. You're going to want to keep track of the image format, and while you're exploring the data sets, you need to ensure that they are consistent. Because as much as I love Coco and I love Pascal or Kitty, they do not consider people the same way. They are not standardized, so to speak, and that's your job. You need to settle on a specific format and decide what constitutes a person, and probably re-annotate your data. So at this point, you're going to want to do two things. One, of course, explore the data. On the one side, to be aware of any biases present there, and on the other, thinking about the limitations of your deployment device. You want to know how your camera performs in different conditions, and if your users are going to be using your app in those conditions. I'm thinking about, for instance, night. Are they going to be at a pub using your phone? Well, then you will probably want to work on night images that may or may not be present in those open data sets. So when you're looking at your data, you want to start planning about augmentations that specifically balance out the limitations of your data. And of course, you also want to analyze that, your data to extract statistics like the mean RGB values, which you will then need on your device to normalize your input data, because that makes a huge difference. So at this point, you have your architecture, you have your stats from the data, you dump that into that configuration file, and you pass it along to training. So who here has already heard about transfer learning? Show of hands. Okay. So for everyone, basically, the idea is that you don't have to start from scratch every time you apply in deep learning. You can, since you're going to be basing things off a classifier, and that classifier has probably already competed on ImageNet, trained weights are already available to you, and you don't have to start from random values. You can start from there and then train either more slowly or not at all that model. So what you do is you download those available weights, you freeze the corresponding layers, and the only part in your network that is going to be actively learning is the detector, which makes everything a lot faster and easy to handle. So before I move on, you're going to be seeing that classifier as a feature extractor that feeds into your detector. And that's what the part you're freezing, and the detector will be the part that you're actually training. So if you notice at this point, you're already tracking tons of things, or you should be tracking tons of things. And the only take-home message from here is choose any tool that you're familiar with, even if it's just spreadsheets or comma-separated values. Nobody really cares as long as you're systematic and you're really, really tracking. And I know that's something that software developers say till they're blue in the face, but it's particularly true here, because you're going to be generating massive amounts of data that you need to validate before you're able to deploy. So at this point, from the training, what you get is your trained weights. That you also serialize, and you pass it on to the rest of the pipeline. And of course, as I was saying, you're going to want to evaluate, because when you're just doing some research, or you're playing at home just for fun to see if you can actually get something running, it's really easy to get excited when you take a picture of someone 10 meters away and you get a head detected, or you get that person detected. And yeah, great, look, at the left, I've got that on red, you can see that both the person and the head have been detected. That's fantastic. And then you train another model, and the head isn't detected. That's a bit less good. Okay, that's fine. But then someone comes along and says, yeah, sure, but did you notice that on that first model, actually the detected head occupies half of the guy's body? That's not really good, is it? So which model's worse? The one that doesn't detect a head, or the one that says a head occupies half of someone's body? Tough to say. It's even worse when you're dealing with confidence values and boxes that are correct-ish but seem slightly off. Because depending on the actual application you're developing, sometimes you only need a rough location of your target, but sometimes you really want to build effects that are almost segmentation-like, and you want very precise bounding boxes. So that makes all the difference, and that's something that you also want to measure before choosing a model as the good one for your deployment on the phone. So what you do is you go full data scientist, another graph of those, where you have your precision and recall curve. Mostly everyone will have seen this. And this is just a sample of the tons of experiments we ran. Every single little dot of that stems from a dozen models. So these are just a dozen of the models that we were testing. And and of course we want it to be on the top right corner, where you have perfect precision, perfect recall. But the way you choose it is through this, and out of the tons of models you've been tracking. But what specifically have you been tracking? One is your architecture. You also have been tracking the different data sets you've been using to train, because you're going to do experiments with certain subsets. You're going to be tracking also what hyperparameters you were applying. Oh, and what augmentations, of course, because as I said before, you wanted to balance out the limitations. So did that augmentation help you, or did it harm you? You want to track that as well. Like as I was saying, also the hyperparameters and deployment parameters, such as the minimum confidence you're accepting. Because if the detector tells you that inside a box there's a 0.3 probability or 0.5 probability of there being a person, is that good enough for you to show it to the user? Will you consider that a person? Because that affects things like running times. Because the more boxes that are returned by the detector, the more boxes that the application built on top is going to have to process. So you need to think that the more restrictive you are, probably the slightly faster you're going to be running. But at the same time, if you're too restrictive, there will be detections that are not passed on to the user. So hopefully, from this evaluation, you've found the best possible combination of architecture and of hyperparameter learnings and hyperparameters and deployment parameters. And that gets tracked as your best possible model. The description of that has stayed in that configuration file, which is what you pass on to the actual device for deployment. And at this point, you have a ton of different options available to you. There's frameworks being announced every day. So this is just a rough, this is just a sample of what's available to you, roughly ordered from highest level of abstraction to lowest level of abstraction. In the case of iOS, well, if you're going to customize every aspect of your network, you're probably going to be working on bare metal or metal performance shaders. But hopefully you'll be able to use a framework that gives you already known architectures, such as mobile nets that you can load with, say, TensorFlow. And the same applies to Android. When you want to develop, you want to try as much as you can to use frameworks that give you high-level APIs that you can use. But on top of everything, or the most important thing here is that from the very beginning, you need to have a very fluid loop, a very fluid iteration between your design, your trainings, and your profiling. As early as possible, you want to have something deployed on the phone. If at some point at the very beginning you only have a classifier, that's okay. deploy that and profile on that. Because if your classifier is already only running at 5 frames per second, there is no way on earth you're going to make the full detector run at 60 FPS. It just won't happen. So when you see that, if you see that within the first week, you can go back to square one and choose a better architecture. So it's really important to keep that iteration going again and again and again until you have it just right. So just a few words at the very end about pitfalls and, most importantly, how to avoid them. Essentially, going back to the data sets, you really also don't want those to be a black box. Of course, you cannot look at billions of images, but what you can do is try to characterize them, find out things like what the general light conditions are, the size of the objects in there. So if you're interested in a series of objects, you want to know if they're all very close up, which means that your final trained model will not deal with faraway distances unless you apply augmentations while training. You want to know if there simply aren't any of the objects you were hoping to find. And you also want to make sure that you're thinking about your device when you're planning those augmentations. So probably in the case of phones, you're most likely going to have problems with light conditions. So start planning what your augmentations are going to be about that. You will also be having problems with the range of the camera, so start planning around that. Oops. So, and of course, I'm going back to the same idea of the automatic configuration, because every time a human tries to do things that should be automatic, things break. That's just what we do. We fail. So it's normal. We just accept that and try to make things as automatic as possible so that we can move to other more interesting tasks. So every single step, from the definition of the network to the statistics of your data, every single steps until the deployment need to be automatically dumped into that configuration file, which is what you pass onto the phone. And of course, trying to mix that data science type evaluation where you're aiming at the best possible precision and recall, but you're also keeping track of how it looks on the phone, whether those bounding boxes look right to a human. Because after all, you have to think about who is going to use the app. And well, again, tracking, and early profiling on the phone. So that's it for now for me. And if you've got any questions, now there's plenty of time to dive into any of the parts that I've been running through. And thank you.
Thank you, Irina.